All right, so today is going to be a bit different. Um, so um, it's going to be different in a lot of ways. For one, I'm going to be writing very little code today. In fact, you guys are going to be writing more code than I actually will be writing today. Instead, what we're going to do is that I'm going to first let me talk about the exam. I have no idea what the grades are yet because they're right now sitting in my office, fully graded but not tallied. Right, so all the questions have been graded, but we haven't added up the points yet, and I have no idea what any specific person did or how they did because I go to pretty good lengths to make sure I don't know how any particular person is doing by making sure we grade an entire everybody on a single page at the same time, right? So that way I'm not going to go through your grade and go, haha, I don't like this student, so you fail. Right. So we try our best to avoid any kind of bias against you. I suppose if I don't like your handwriting, that could be one thing, but yeah, that's about. So I don't know how you did, but I can say that most people did. So the TAs took some questions. I took some questions. I can say that basically that the vast majority of you got between 16 and 20 points on the analysis. So you did very good on the analysis. A couple people did the extra credit correctly. And I did read the surveys. The surveys were extremely helpful. So one thing that I did do is that, as you'll see up here, I moved my myself to the top right. Somebody pointed that out, trying that out so that they could see the camera, because one of the most common requests I got was, hey, can we put timestamps in the video? And yeah, I suppose that's possible. It's just more work for me. In fact, what's easier for me is to instead stop recording when we finish a topic, and then start recording another video on another topic, that thereby breaking the video up into a single lecture up into multiple digestible chunks, right? I guess technically I get more views that way too, so hacks. But no, really, that's what I'm doing for 1068, where I'm doing a couple of what are called flipped lectures. Now, you'll be doing some of these once come after spring break, because after spring break, let's see, around the end of March, beginning of April, I will be out for a week. But that does not mean that you do not have class. In fact, what will happen is I'm just going to pre-record a bunch of lectures for you. And then instead what's going to happen is that you're going to be expected to watch those lectures before you come here. And this lecture will be treated as essentially an additional lab section. Your TA will be, or ATA will be here supervising basically this, and you'll have some problems to work on. And it's going to look something along what's going to happen today, which is that we're going to talk about your homework on recursion. So I didn't want to get too much into trees, which is the next topic, because right now we're pretty much done with recursion, and I could have started that on Monday with the morning class, but I decided not to, because then we'd actually start getting into the code, and then we'd forget halfway through where we were with the code when we got back to spring break. So we'll start with the code back in when we come back. Instead, what we're going to do is that we're going to use the time in class to work on some recursive problem. We'll see how many we can do. Probably just one, because it's going to be a rough one. But I'm also going to go over the homework that I'm giving to you guys. So I posted it online, and I did not go into much detail on the second part of it. The first one, yeah, I went into tons of detail. The second part, I just said do this. And I gave you, I think was an uncharacteristically little amount of guide. So here is your recursion problem. In case you're wondering, I do all my homework typing and all my assignments and all my documents in LaTeX, which just means that I end up having to compile my paper and my assignments as well. So that's here's where we are. So okay, so today your homework will be working is puzzles. Now the first thing you gotta know is how this plays into spring break. This is not due over spring break. This is due the week after you come back from. So this is due, let's say, not this week. So not this Friday, right? You're technically getting it this Thursday and Friday. It's not going to be due here. It's going to be due like on, yeah, I think I said the 17th. I assume that you're going to do very, very, very little work over spring break, and so I plan accordingly. Okay, I expect you to work basically as much as I will, which will maybe be a couple of hours haphazardly at the end of it, or possibly responding to some mad emails. Anyway, so first and foremost, one of the problems I'm going to go over has been done to death. It has been given as a homework problem for 50 years or something like that. Okay. That being said, so obviously that means you could potentially look up the answer online and cheat. Don't do that. I mean, aside from the whole copying other people's work, you're not going to understand it when you do it that way, and you're missing out on basically understanding how this beautiful technique that really works really, really well. You've already used it once to solve the mazes without actually using recursion. And now we're actually going to get into using recursion rather than using a stack. But it's the same strategy. What we're going to do is we're going to go over this strategy today and see how we can use it to how it applies to so many different kinds of problems. And we're going to do it on 2 puzzles. The first thing is basically we want to so this is broken up into 2 parts. The first part is chess. The second part is Sudoku. You get the choice of solving one of 2 problems. And I'll go back over to the front page in a bit to go over our algorithms and how to solve these problems. You get to choose between one of 2 chess problems first. The first is the 8 queens problem, which is the one that's been done to death. So for those of you who play chess, this is a pretty easy to understand problem, but I'm going to go over it as though you don't know what chess is, which is so imagine a chessboard the same as a checkerboard, white squares, black squares, right? Except that in checkers it would be red. So the queen is the most powerful piece in chess. In chess, the queen can basically move any number of squares or in a horizontal row, a vertical column, just like a rook can. But on top of that, she can also move like the bishop, which means she can move diagonally as well. So the 8 queens problem basically doesn't really you don't really need anything more than that for chess. The 8 queens problem says, given a chessboard, an n by n chessboard, in this case an 8 by 8 chessboard, let's put 8 queens on the board in such a way that none of them can capture one another, right? That means that none of them can, and in chess you capture pieces by basically smashing your piece into the opponent's piece. So that means that so here's a solution. In this solution, no 2 queens occupy the same row, the same column, or the same diagonal. Okay, that's the puzzle. Basically, place 8 queens in such a way that that none of them occupy the same row, column, or diagonal. And that means that none of them will capture each other. In case you're wondering, if you don't play chess, that you get 1 queen on each side. 2 if your opponent is terrible and you manage to promote a pawn to a queen. I suggest using an 8 by 8 integer array to represent your chessboard. Here's an example solution there. You don't have to generate all the solutions. You just have to find one. Once you find one, you are done. And I have a hint down here. Basically, just remember that only 1 queen can be placed in each column. This means you can simplify the problem a bit by asking, for this current problem, which row can I put a queen on safely? So, and that just will get into the recursion of this. But this is just one possible chessboard. Also, interestingly enough, I don't believe it is an image. I think it's something that was managed to be generated by my source code. So, or it is something that I generated with my source code. So that's the easier problem. You can select either one of these to do. The other problem is the Knight's Tour problem, which is more challenging only because for an 8 by 8 board, it's a pretty big problem. So if you want to try it instead and want to make it just as easy, try it on maybe a 4 by 4 or a 5 by 5. So the Knight's Tour says we've got this piece in other piece in chess called a knight. And a knight moves really weird. It moves in this kind of L shape, and it jumps over other pieces. There are no other pieces on this chessboard, so don't worry about that part. But it moves really weird. It moves 2 spaces in one direction, in one axis, and then 1 space in the other axis. So it can move 2 up and then 1 to the right or left, or 2 down and then 1 to the right or left. Or it could move 2 to the left or the right and then 1 up or down. So all the possible images, so it's 8 possible moves, all of which are basically shown here. it creates a kind of L, so it's kind of an L move. So the question is here. We place our knight somewhere down on the chessboard. We want to write an algorithm that lets him travel on each square exactly once. Okay? So the idea here is that we place the knight on the chessboard and we move him until he visits every single square on the chessboard exactly once. It's visited once you visit a square once you land on it. So for instance, the knight might go here for his first move, then here for his second move, then here for his third move, and then here for his fourth move, and then for his fifth, and then for his sixth, and then for his seventh, then for his eighth, and so on and so forth. And the idea is that basically you want to visit all the squares, and as you can see, just trying to figure it out, it's very possible that you can land yourself into hot water by just getting to a dead end, which sounds like you might have to backtrack or something to find a solution. Okay, so you've got your output should probably like be the chessboard, like an 8x8 array, but basically each value in the array is the order at which that square was visited. So this would be 1 or 0, depending on how you count it, then 1, then 2, then 3, and so on and so forth. So you can choose one of those two problems, and you can use the same general problem to solve both of them, which we'll go over, which is this recursive backtracking algorithm. The other problem is Sudoku, okay, which is write a problem that can solve a Sudoku puzzle. You can put the puzzle you want to solve into your source code as a 2D integer array, which means you don't have to read it in or anything like there. You can just hard code whatever puzzle you want to solve into your array, into your source code. So the idea here is that you want to, and we will solve this using the same recursive backtracking algorithm that was using the 8 queen problems. So what is Sudoku? Well, let's look at the extra credit to find that out, which should be, okay, I guess that, oh right, because it's not a clickable link because that reader doesn't do a clickable link. There we go. So Sudoku is a Japanese, it's Japanese for number place, and it appears basically in the puzzle section of your newspapers, just like the crossword does these days. So it's a very popular puzzle. We don't know really where it came from, but the object is to replace all the blanks in a Sudoku puzzle, or zeros as they're formatted here, such that, and it's a 9x9 grid, such that every row, column, and 3x3 box contains each of the digits 1 through 9. So here's your typical here's a starting puzzle, and here's the solution. So if you look at the solution, you'll note that basically every row has all the numbers 1 through 9 exactly once, all the columns have 1 through 9 exactly once, and all the 3x3 squares that are sectioned out have each number exactly once. If you want to see this in an actual kind of puzzle that was easy to look at, which we'll use, we're going to go to the New York Times webpage to see that. So every day they have a new Sudoku puzzle, and the idea here is that every actual Sudoku puzzle will have exactly one solution. Okay, given these numbers, give me a unique solution to these. Okay, so I can put a 1 here. Oh, no, I can't because there's already a 1 horizontally over here. Can I put a 2 here? Yes, I can. What about, like, say, 3 here? Can't because there's already 3 in this row. Okay, what about a 7? Can't put a 7 there because there's a 7 in the column, and there's a 7 in the same 3x3 grid I occupy. That's actually the hardest part I find about the puzzle once you understand the recursive backtracking, is figuring out how do I check if I'm in the same 3x3 grid. And the answer to that is to use some modular arithmetic to do that. Some division and some modular arithmetic should sort that problem out for you, I believe. So the extra credit is, so there's this text file here which contains 50 of these Sudoku puzzles, right? Read in the text file, read in all those 50 Sudoku puzzles, solve them all, and then prove that you solved them all by adding the top 3 numbers of each, the top left 3 numbers of each puzzle and add them together. And then basically that's your answer. So just to prove that you solved them all. Yes?
Is it like add 483 and then combine it, or
add 483 to 200 and whatever, and then whatever this is, and then whatever 30 this is, right? So you add all the top. So it's treat each of these as a 3-digit number. Okay, and that's extra credit, which is worth a whopping 10 points today. Which is pretty significant because most of the extra credits worth 5, I think. Yes.
Did you have the top left of each other, like all 50 together?
Of all 50 together to show what the answer is, right? So so basically you can choose to do, and I mean, if you solve the extra credits, given that you've already solved that one. So essentially you can choose to do it easy, or you can choose to do the hard version, right? Again, so yes.
Can we get the answer just so we know when we do it?
So if you make an account on Project Euler, right here, let me log in and give it the confirmation code 72659. Right, if I go to problem 96, which I believe is the one here, there will be a place for you to submit an answer, and you submit the confirmation code, and it will. So if I hit, maybe it's 5,637. I doubt it is. That doesn't seem like a big enough number, but I can just type in a confirmation code here. It says it's incorrect, and once it's correct, it will tell you. You can. And once you get a problem correct from Project Euler, it opens up a. There can be sometimes they'll have a PDF that accompanies ways that you can solve the problem, and then also it will open up an accompanying forum. That basically people can discuss their answers. So because I haven't solved these ones, they're closed to me, right? Once I solve them, they open up. So that's the overview of what you need to do. So I'm going to quit this and then start another video.